will be a poster presentation. So let's see. The first speaker will be Alessandro Thibault from Aalborg University, and he's going to present a paper from statistical model checking to runtime monitoring using a Bayesian network approach. Anand, are we ready?
Hi everyone, I am Alessandro Thibault and I am an assistant professor at Aalborg University. This work I'm going to present is a joint collaboration with Manfred Jäger and Kim Larsen, also from Aalborg University. Now I'm going to introduce the main component of our framework along with the core idea. In this work, we link statistical model checking with machine learning. Let's assume that we have a system modeled as a stochastic time automaton and implemented in the UPAL SMC software tool. Let's also assume that for this system we are observing a set of interesting temporal properties. A Bayesian network is then used to learn the joint probability distribution over this set of properties. And finally, we can perform real-time queries from the learned distribution. Let's start with stochastic timed automata. A stochastic timed automaton is a stochastic finite automaton enriched with real valued variables called clocks. The clocks measure the progress of the time which elapses while an automaton is residing in some location. The top left figure depicts a simple safety critical scenario. Here a car needs to cross over the bridge, while at the same time a ship wants to pass under the bridge. However, for the ship to make the passing safely, the bridge needs to be open. Conversely, the bridge needs to be closed in order for the car to safely cross over the bridge. Obviously, the bridge is only allowed to be opened in case the car is not over the bridge. This scenario can be represented with two stochastic time automata in UPAL, one for the car and one for the ship. The stochastic time automata for the car is depicted in the bottom picture. Car and ship have two different clocks, and also we assume that car and ship have to wait for a certain time before crossing the bridge. In general, model checking for stochastic time automata is undecidable. Therefore, we need to use statistical model checking. In some cases, we are interested in more refined performance analysis of a system. For the bridge scenario, for example, we will be interested in the probabilities that the car or the ship finishes first. For the queries to be meaningful, we need a stochastic semantic of networks of timed automata. In UPAL SMC, for example, delays of components are by default resolved by a uniform or exponential distribution. On the bottom of this slide, we explicitly report the UPAL SMC model for the car. The one for the ship is similar. As we can see, for locations and transitions, we have some time constraints, which define either uniform or exponential delay distributions. For collecting the values of the temporal properties we are interested in, we are using monitors. In this work, we are considering categorical properties. So, for any run of the system, each property can get a value from a finite domain. We further assume that each monitor reaches an absorbing state with probability 1. For our bridge example, we are considering for each location W, B, C, and AND the categorical properties psi s, all with domain in a car or ship. We define each property such that psi s of pi is equal to car if and only if, in the run phi of the system, car is the first to reach s. The figure on the bottom of this slide shows the monitor for these four properties. By combining general stochastic time automata and monitors, we obtain probabilistic queries that are undecidable and therefore outside the reach of the exact probabilistic model checking. That's why approximate estimation techniques like statistical model checking or Bayesian network are required. For some property observation, we can use a Bayesian network to learn the joint distribution of those properties. The properties here are represented as nodes in a graph. We perform then a structured learning algorithm to learn the dependencies between the nodes in the graph. That is, we find the best configuration of edges for the graph. Through the structured learning algorithm, we have the capacity to discover non-trivial dependencies between properties. Once the structure is learned, we learn the probabilities which define the joint distribution. The learned Bayesian network can now be used to compute conditional probabilities. Let us consider 4 binary properties as an example. Initially, the probabilities of the properties are distributed as shown in the left picture. In each of the nodes of the graph, the top red and the bottom green bars represent the probabilities of the 2 states of the properties. Let's now assume to observe psi2. And to the right picture, we show how the probabilities change according to the observation. We stress the fact that we have a lot of flexibility here. In fact, we can condition the joint distribution on any properties and in any order. Now, I want to introduce the framework we propose. In our framework, for a system represented, for example, by UPAL, we assume to have access to a set of categorical path properties we are interested in, represented by monitors. We run then case simulations of the stochastic time automata representing our system, and as the model runs, we collect the data of the properties into a table which has size k times n, where n represents the number of properties we are observing. From the table where the observations are collected, we learned both the structure and the parameter for a Bayesian network. Finally, the Bayesian network can be used to query the probability distribution of any of the properties given arbitrary observation of other properties. We point out that the Bayesian network not only allows us to discover non-trivial dependencies between properties, but it can also be used to efficiently update probabilities of unobserved properties given real-time observations. The Bayesian network can be used in 2 setups. The first one is the runtime forecasting. Let us consider again the bridge example. The picture to the left represents the Bayesian network learned on the 4 properties we monitor in the bridge system. I briefly recall that each property represents which, among current ship, arrives first to a certain location. Let's focus on the right picture. And now we are interested in monitoring which among car ship is going to arrive first at the end. At first, when no observation is available, the probability that the car arrives first at the end is slightly above 50%. Later, we observe that the car arrives first at the waiting queue. So the probability of phi hand changes. After a few more seconds, we observe that the ship passes under the bridge before the car, and phi hand is changing again. Finally, the ship is observed to be right after the bridge, which confirms that the ship, for this example, will arrive first. The second setup we can use the Bayesian network in is the diagnostic prediction of unobservable properties. In other words, we can use Bayesian network to make predictions of unobservable properties based on what we could observe. For the bridge example, let's assume that only phi end is observable, maybe because we only have a camera at the end of the road. So, at some point, we observe that the car arrives first at the end. We can use the Bayesian network then for trying to explain whether or not the fact that the car arrives first was due to the fact that the car was first in the waiting position. Now I want to show the results of some experiments. We consider now a more complex set of properties for the bridge example described in the previous slides. We now define a new set of properties. For each location and for car ship, we define psi car S and psi ship S. Each takes value in 2 discretized time intervals domains, t_car_s and t_ship_s. For example, if we observe that psi car b is equal to t3, it means that the car has arrived at the bridge at time points 19.2 and 28.6. In addition to the new properties, we also retain the property phi hand with domain car or ship that encodes which among car and ship arrives first at the end location. Again, we collected into a table the values for all the properties by running 10,000 model simulations. The resulting Bayesian network depicted in the picture shows a more complex structure with respect to the one that we had for the simplest scenario. Let's imagine that we are interested in monitoring the real-time evolution of the probability distribution over the arrival time of the car, as new properties are observed. At time t0, you observe that this probability is uniformly distributed over the 10 possible categorical values. At time 1, we observe psi car w, and by conditioning the original probability distribution, we observe that the distribution of psi car n has changed. Finally, at time t4, we have conditioned psi car n with respect to 4 observations, and we can notice that most likely the car will arrive at the end before the interval t6. Finally, we estimated the time per query by averaging the query time on 10,000 model traces, which results to be 0.08 plus minus 0.05 seconds. Those results confirm that the Bayesian network query can keep up with the speed of this real-time application. We investigate the accuracy of probabilities calculated with the Lair Bayesian network, and we compare it against the accuracy that is obtained by statistical model checking using a comparable amount of data. Again, those results are obtained for the bridge scenario. We consider the conditional probabilities distribution that the car reaches its destination first given the arrival times of car and ship at the waiting and bridge positions. For the conditional variables, we identify a rare and a common joy configuration of time intervals. The rare and the common configuration occur approximately 1,000 and 6,000 times respectively in a sample of 1 million traces. We estimated the true query probability by repeating test simulation over 1 million traces each. Since the standard deviation was negligible, we can treat the obtained estimate as the ground truth probability. We learned Bayesian networks from different sample traces ranging from 50 to 600,000. Similarly, we also estimated the same probabilities with UPL-SMC. The probabilities obtained for the two different queries are plotted in the two figures below. The left and the right figures show the rare and the common configurations, respectively. The estimated probabilities with Bayesian network and UPL-SMC are colored in blue and orange, respectively. In green, we have the true probability. Here, there is a number of observations that we can make from the plots. We see that even for large sample sizes, the width of the statistical model checking confidence interval for the conditional probability decreases only very slowly. The point estimates obtained from the Bayesian network converge to the true probability much faster than statistical model checking point estimates, where statistical model checking suffers from the smaller number of samples that will be relevant for the query probability. The Bayesian network estimates are less affected by the rarity of the observed values, since its probabilities are derived from a combination of empirical frequencies and inferred conditional independence relationships. Now we draw some conclusions. We have introduced a framework which links statistical model checking with machine learning. We exploited Bayesian networks to learn dependencies among interesting temporal properties of stochastic time automata. Bayesian networks are very efficient for real-time updating of probabilities of unobserved properties, as new properties are observed during the evolution of a real-time system, and the estimated probabilities are at least as accurate as what is obtained from UPL-SMC. We want to mention that it would be an interesting subject for a future work to learn also a set of interesting properties rather than defining the properties a priori. This research direction may lead to strengthen the connections between the machine learning and the statistical model checking domains. Thank you for your attention, and I will be happy to answer the questions you might have.
Thank you. So now you have a chance to ask Alessandro some questions. You can just raise your hand in Zoom, or you can drop your question in Slack or in the Zoom chat. I can see there are already 2 questions. The first one, both of them are by Gio. The first one is, Gio, do you want to repeat?
Yeah, I can repeat the question. I can't raise my hand because I'm a co-host, so I'll just abuse my privilege here. So my first question is, if the properties that you are monitoring, if they are somehow related, then does the Bayesian network kind of discover this dependence on its own? So as an extreme example, suppose you have like phi and not phi, both as part of your specifications, what happens?
Well, if you have phi and not phi as if you define such properties, so for example, not to visit some specific location or visit some specific location, probably the Bayesian network will learn 2 states that are completely independent to each other.
Okay. And in other cases, like, can it learn something about the structural dependence, or maybe the properties have some common predicates or some common operators? Who can it learn these kind of relations? That would be quite interesting.
I mean, when you have your set of properties, right? So you have to define your set of properties you are interested into. Mm-hmm. Then you have those properties, and then you can actually learn the structure. So you are learning how those properties are related to each other. So you can find both the dependencies and the independence. So you can actually find out whether there are some, let's say, strong connection among some subsets of properties or not.
Mm-hmm. Kim, I think you're muted. We can't hear you.
I just wanted to add, when we talk about dependencies, of course, this has to do with conditional probabilities. So 2 properties are conditionally independent if the conditional probability of one with the other one is just the same as the probability of the first property, right? So that's
right.
The definition of dependency.
Sure. Yeah. Yeah, I can let somebody else ask a question. Otherwise, I can keep asking.
I don't think anyone else is raising their hands, so feel free to go ahead.
So one other thing I looked at in your experimental results, it looks like the Bayesian network estimate kind of oscillates around your true probability value. So one question would be, is it possible to somehow modify the approach so that it's like a strict under approximation or a strict over approximation?
Which experiment are you referring to? Sorry.
The plots that you showed on the slide, like towards the end, for the rare and common case. Yeah.
Yes. So can you say that again, the question?
So the probability estimate from the Bayesian network, it seems to kind of oscillate around the real probability. So if I were to want to stop at any time, one nice feature to have would be that the probability is always a strict under approximation or a strict over approximation, right? So is it possible to do that? I don't know. I'm just curious to know.
So if I understand correctly the question, you want to have some guarantees that at the very end you converge to the true probability, right?
More about before you reach the end. Is it possible that you always stay below the actual probability, or always stay above the actual probability threshold?
Well, that depends, because you may be when you are using Bayesian network, you may be below or above the true probability distribution that you are trying to estimate. Mm-hmm. But in the end, you may converge to the right value. So what we wanted to show in that experiment, that you are much faster to reach to approximate the true probabilities the true probability than statistical model checking.
Okay.
Maybe Manfred, you want to say something?
Maybe I can add to that. So of course, you cannot have always under approximations or always over approximations, because probabilities sum up to 1. So if you under approximate
Right.
the conditional probability for not phi, you will over approximate the conditional probability for phi. And a priori, the Bayesian network has no, let's say, way of distinguishing phi or not phi.
I see. But is there some way to kind of add up some prior information that allows it to do that?
Well, you could, let's say, if you are focused very much on one particular property and maybe one particular query, so you want maybe the conditional probability of phi given psi, then you could certainly modify the learning algorithm such that you are sure to underestimate, or almost, of course, there's always a little bit of statistical uncertainty there. But you could modify the learning algorithm in order to be sure that you rather underestimate that probability. But our framework is really made for flexibility in querying. That means that a priori, we don't want to fix what are the things that we observe, what are the things that we query, and therefore we have a symmetric view on phi and not psi, phi and not phi.
No, this is very interesting work. No, thank you for the talk. It was quite interesting. Yeah. Thanks.
If you have any more questions, you can still send a message to the authors. In interest of time, we will just continue to the second talk now. And the second talk is by Changwei Lin from National Taiwan University. And it's called Efficient System Verification with Multiple Weakly Hard Constraints for Runtime Monitoring.
Hello everyone, this is Changwei Lin from National Taiwan University. Today I will talk about our work, Efficient System Verification with Multiple Weakly Hard Constraints for Runtime Monitoring. This is a joint work with my student Wu Shilun, Bai Jingyuan, Zhang Kaijie, Xie Yiting from National Taiwan University. And it is also with Huang Chao and Professor Qi Zhu from Northwestern University and Professor Imsa Kang from CMU. The motivation of this work is actually from automotive system. We know that there are periodic tasks and messages within the system. For example, we have tasks running on electronic control units. We have messages on in-vehicle networks, such as controller area network or time-sensitive networking. Furthermore, because of the development of connected vehicle, we have vehicle-to-vehicle or vehicle-to-infrastructure messages, and usually they are safety-critical messages. However, we know that faults exist. It is because fault-free systems are very, very expensive. Or even worse, fault-free systems don't exist. For example, the wireless network, we cannot prevent fault. However, with the fault, we still want to guarantee system safety. Can we do that? In this work, we use weakly hard model to model fault. A weakly hard fault model is captured by an MK constraint. It means there are at most M faults or bad events among any K consecutive events. Here, a fault can be very, very general. It can be a deadline miss, a message is missing, or if we consider security, it is a message without authentication, or a malicious attack. So the problem is, given a system with faulty input modeled by the MK constraint, is the system safe? We can use the following example to explain it. For example, you have two weakly hard constraints, 1, 2, and 2, 100. Which one is better for the system? You may argue 2, 100 is better because there's only 2% of fault, and 1, 2 means 50% of fault. However, 1, 2 by definition, it means there is at most one fault among any two consecutive events, which means there will be no two consecutive bad event or two consecutive fault. No, it doesn't exist. However, if you consider 2, 100, it means it is possible to have two consecutive events. Then the system may go to an unsafe state if there are two consecutive faults. So I think the answer here is it depends on the system. We cannot say 1, 2 or 2, 100, which one is better for the system. And this is something we want to verify in this work. Here, we want to emphasize two very important implications in system design. The first one is if the environment ensures that the fault occurrence satisfies certain MK constraint, then we can verify the system is safe. Or if the system cannot ensure that the fault occurrence satisfies certain MK constraint, then we will need a runtime monitor to monitor the occurrence of fault. And if we observe that, if the runtime monitor observes that some MK constraints are violated, then we should adapt the system to a safety mode or more conservative mode. For example, if it is an automotive system, maybe we can say the automotive system should stop. So this work will be able to support definition of requirement of the environment, and we can also guarantee safety with faults and limited resources. There are also some other objectives behind verification in this work. For example, when a fault is a deadline miss, our work can actually find the most deadline misses but still guarantee system safety. Because we can allow some deadline miss, we can reduce computation and communication load for resource saving, and this is something that real-time system community does. Also, if a fault is a message without authentication, for example, it's a system with partial signing, our work can find the most messages without authentication but still guarantee system safety or security. Similarly, because we don't need to sign or authenticate all messages, we can reduce computation and communication load for resource saving. On the other hand, if a fault is caused by a malicious attack, from the perspective of the attackers, our work can actually find the least deadline misses or compromised messages, but still let the system become unsafe. So this is from another perspective. We want to crash the system. And based on that, we can reduce attacking cost. Because we don't need to attack all messages, we just need to attack some messages. So the problem in this work is, given capital K and a system with faulty input, modeled by weakly hard constraint, we want to verify if the system is safe with each MK. Here, lower k is smaller than or equal to capital K. The problem is equivalent to constructing a safety table as shown in this figure. This example is a safety table with capital K equal to 8. We want to explain the objectives behind verification first. If we construct the safety table as shown in this figure, actually we can find the optimal strategy for system designer. It is 1, 2, 2, 4, 3, 6, and 4, 7. That means if we can guarantee the environment satisfy 1, 2, 2, 4, 3, 6, and 4, 7, we can guarantee the system is safe. On the other hand, from the perspective of attacker, we can also say 1, 1, 2, 3, 3, 5, and 4, 6 are the optimal strategy for the attacker. Because, for example, if the attacker wants the system to go to an unsafe state, it just needs to attack 3 messages among 5 consecutive messages. It doesn't need to attack 4 messages among 5 consecutive messages. That's the meaning that we say 3, 5 is a local optimal strategy for the attackers. So, what a runtime monitor should monitor? Actually, it needs to count the fault. For example, if the monitor counts the number of faults, and it can guarantee that the number of faults is still in the safe region of this safety table, then we can guarantee the system is safe. However, if the monitor observes that the occurrence of fault may fall in the unsafe region, then we know the system may be unsafe. Then the system should switch to a safety mode. Then, how to construct safety table? We want to introduce some observations first. The first one, we can directly check the figure, so it is for the left direction. If we know that the system is safe with 3-6 weakly hard constraint, then we know that the system is also safe with 1-6 and 2-6 weakly hard constraint. This is because 3-6 means there are at most 3 bad events among 6 consecutive events. And if you consider 1-6 and 2-6, there must be less bad events among 6 consecutive event compared with 3-6. So if 3-6 is safe, then 1-6, 2-6 are also safe. The second observation is for the right direction. Again, we can use the example to explain it. If we know that the system is unsafe, given weakly hard constraint 4-6, then we also know that the system with weakly hard constraint 5-6 and 6-6 are also unsafe. This is because 4-6 means there are at most 4 bad events among 6 consecutive events, and if the system is unsafe with it, then 5-6 and 6-6 may have more bad events, so the system is also unsafe. The third observation is for the top direction. Again, if we know that the system is safe with weakly hard constraint 3-6, then we know that the system is also safe with weakly hard constraint 3-7. This is because if we know that the system is safe with 3-6 means there are at most 3 bad events among 6 consecutive bad events, then when you consider weakly hard constraint 3-7, it means there are at most 3 bad events among 7 consecutive bad events. It is a better scenario, so the system must be safe if given 3-6 is safe. There are actually more observations. If you are interested in them, you can check the paper, but the most important thing here is if we want to construct the safety table, we don't need to check all pairs of MK. If you agree that we don't need to check all pairs of MK, we can introduce the following 3 approaches. The first one is the monotonic approach. We can check this example. You can just follow the arrow, and we only need to check the weakly hard constraint gone through by the arrow. You can see that we only need to check at most 2k weakly hard constraint, where k is the capital K. It is 8 in this case. Compared with checking all pairs of MK, of course, it is more efficient. The second approach is the monotonic approach with dynamic upper bound. In short, it uses more implication so that we can check less weakly hard constraint. In this example, if we know that 2-3 is unsafe, then we can imply 3-4 is also unsafe, and we don't need to check 3-4. The third approach is lowest cost first heuristic. Actually, we don't need to pick MK by some order. It means it doesn't need to be monotonic. We can jump within the safety table. Based on this observation, we can pick MK based on some estimation of verification cost. For example, the time complexity of verification. Based on the estimation cost, we can pick the lowest cost and verify that weakly hard constraint first, and apply those observations to imply other weakly hard constraint. Here, we want to talk about a special case. If the system is modeled as a finite state machine, and we want to verify the reachability property, then we can make the safety table construction more efficiently. More precisely, the complexity of constructing the safety table is the same as that of verifying a single MK, where K is a capital K. So, amazingly, the complexity of checking all pairs of MK is the same as checking one single MK, where K is a capital K. This is done by approach, layer BFS approach proposed by us. The basic idea is, given a fixed K, we add edges constrained by M when moving from layer M-1 to layer M. So in short, it is still similar to a BFS approach, but when we pick the edges to be added into the graph, we need to follow some order, and this order is decided by the MK constraint. Our case study is done by a discrete second-order controller under perturbation attacks. The goal of the controller is to maintain a variable x at 0, and the goal of the perturbation attack is to let x outside the range defined by xmin and xmax. And this is exactly the property we want to verify. The system is safe if x is in the range of xmin and xmax, and it is unsafe if it is outside of the range. The fault occurrences here is attacks are constrained by MK, weakly hard constraint. We have state dynamics and then we can transform the state dynamics into state transition so that the system can be modeled by a finite state machine. In the following experimental result, we will use Q as the number of states in the finite state machine. This number is depends on Xmin and Xmax. This is the safety table we got. We used the monotonic approach. The monotonic approach with dynamic upper bound, the lowest cost first heuristic, and the layer BFS approach. All of them get the same safety table as shown in this figure. This is the runtime of different approaches. We can see that the brute force approach, which checks all pairs of MK, the runtime increase very fast, so it is outside of the range when Q is very large. And then we can see that the monotonic approach is more efficient than the brute force approach, but monotonic dynamic with dynamic upper bound is more efficient than the monotonic approach. Besides, the lowest cost first heuristic and the layer BFS approach are also very efficient. Of course, we should emphasize that the case study here is reachability analysis with finite state machine, so the layer BFS can be applied. But if it's other system, other model of computation, and other property, we cannot apply layer BFS approach. Conclusion, we have used a weakly hard model to constrain the occurrence of faults in system input. Then we develop approaches like monotonic approach, layer BFS approach to verify property for multiple weakly hard constraints, so that we can define weakly hard requirement for the system environment. Then we can design a runtime monitor based on those weakly hard requirements. Future work includes different properties such as linear temporal logics under weakly hard constraint, or other models of computation under weakly hard constraint. And furthermore, we can further explore the lowest cost first heuristic. I think there are many different perspectives we can consider in the cost estimation. Thank you very much. If you have any question, please let us know.
Okay, thank you. You will now once again have the chance to ask a question. Okay, go ahead. I can see you raising your hand in the video. You're muted. We can't hear you.
Okay, thank you very much for the. Perfect. So maybe a question for clarification. Sorry for that. But in your complexity bounds, you had on slide 9, but whatever, you had capital X and capital K. What was the capital K? What was that?
Okay. So capital K is given. So if capital K is 8, we want to verify all weakly hard constraints.
But how does it relate? How does it relate to the size of M and K on little m and little k? I mean, is it an upper bound on the number of events you're looking ahead, or?
You mean okay? Lower m must be smaller than or equal to lower k. Okay, and the lower k must be smaller than or equal to capital K. So capital K should be.
And what about capital X then? Because I'm wondering whether you have a pseudo-polynomial algorithm or whether you have a real.
You mean capital X, right?
Yeah.
Yeah, capital X is usually a complexity of verifying one single weakly hard constraint. Yeah, and in this case, it's usually 2 to the power of lower k times the number of states.
So the number of states in your automata could be exponential in the encoding of the number of faults and the number of events.
Okay, to verify single weakly hard constraint, okay, yeah. the complexity is exponential to lower k.
Okay.
Yeah, but it should be polynomial to.
I will look up more in and maybe another question. I was thinking, what about time? I mean, now you have number of faults within some events, but there's also a notion called time. You could think of a number of events in some 10.1 time units or whatever, right?
Yeah, I agree. But so far we just model the event as discrete event. Yeah.
Okay. Thank you very much.
Okay, there are 2 more questions. One in Slack from Rongu. The question is, what are events in a real system? Does this method only apply to systems whose execution is considered of a sequence of discrete events?
Yeah, I think at this point, I think the answer is yes. So the basic idea is, for example, if we have a connected vehicle, so we expect we will receive message, for example, every 100 milliseconds. Yeah, then we can design a runtime monitor, say, oh, do I receive a message right now? And then if I receive a message right now, I expect I will receive a message in the next 100 milliseconds. Maybe there is some error, but I should receive a message around 100 milliseconds from now. If I don't receive the message, I will count this as a fault. Yeah, but it doesn't mean the system will go to an unsafe state. So we need our approach to make sure if we don't receive this message, or like at most M, if we miss at most M messages among K expected messages, will we go to an unsafe state? Yeah, and this is a discrete event at this point.
Okay, great, thank you. Okay, one last quick question. Sebastian Schirmer asks, how can one infer that the state MK is safe or unsafe?
Okay, so yeah, more precisely, I should say the system is safe or unsafe with weakly hard constraint on input. Yeah, so the safe or unsafe is system. Yeah, and the weakly hard constraint is on the input.
Okay, the question is, how do you infer whether something is safe or unsafe in this regard?
Okay. So this is okay. In our use case, okay, it's because we model it as finite state machine. So safe is a state of state, and unsafe is a state of state. And it is unsafe if the system may reach an unsafe state. And if it always inside the safe state, we call the system is safe. Okay. And for general system, maybe, yeah, we can have a more general concept. It can be a property, any property we want to verify. If you can find in our use case, we just focus on finite state machine and retrievability analysis. But if you have some approaches to verify a system under a single MK constraint, we can apply our monotonic approach to verify multiple MK constraints. Yeah, and in our work, we don't specify how to solve general property and a general system model, given a weakly hard constraint. We only for a single MK constraint, we only consider finite state machine and retrievability.
Okay, great. I think this clarifies it. Thank you. If you have any more questions, please feel free to contact him. We will now go on to the last presentation today, which is the poster presentation by Isaac Mackey from the University of Santa Barbara. And it's called Service Provisioning Using Verification Techniques.
Hi, my name is Isaac Mackey. I'm presenting a poster about service provisioning using verification techniques. This is work completed by me and my advisor, Jingwen Su, at the University of California, Santa Barbara. The following example application provides a setting for our problem, a cloud computing service subject to business rules. Consider a company that manages cloud computing resources as a service. Using business processes, users request computing resources, submit jobs, make payments, and receive a receipt for their payment. The sequences of these processes constitutes an enactment of the service. Additionally, the cloud computing service is subject to timed business rules, like answer requests within X days, or receipts should be given within Y days of payment. This leads to our formulation of the service provisioning problem. We want to detect violations of business rules at runtime. Our technical approach for doing this is to express business rules in a formal language, translate this language into linear temporal logic, generate finite state machines from LTL formulas, and use the service enactment as input for finite state machines. Then, the finite state machines indicate the status of rule violations. There are known algorithms for steps 3 and 4, so we focus on steps 1 and 2 in this work. First, the challenge of expressing business rules. We use a logic language of our own design. Rules in this language have two parts. a body, and a head, each a conjunction of inequalities. We require that the body and head share at most one variable. Consider this example rule. When the user initiates a request process at time x, a compute process at time y, such that y is no more than 3 days later than x, and a pay process at time z, such that z is no more than 10 days later than y, and no more than 20 days later than x, the user should receive confirmation through a receipt process at time w that is no later than 10 days after the time they paid. The semantics of these rules are: a rule is satisfied if every satisfying assignment of timestamps to variables in the body can be extended to satisfy the head. For example, if a user submits a request at time 0, a compute process at time 3, and a payment at time 7, the rule is satisfied if they receive a receipt no later than time 17. Alternatively, when a user's activity satisfies the body constraint and no corresponding assignment exists for the head variable w, the rule is violated. The second technical challenge is translating rules with arithmetic and inequalities into LTL. To do this, we use the next, future, yesterday, and past operators. We start by translating inequalities over two variables. Consider the constraint compute at y and pay at z, such that z is less than or equal to y plus 10. We translate this using propositions compute and pay, 10 next operators, and a past operator. When the constraint is acyclic, that is, its graph representation does not contain cycles, the translation is recursively defined using the following technique. First, we translate the constraint between request and compute as request and next, 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 future compute. Then, we translate the constraint between compute and pay and insert the result where the compute proposition occurs in the first formula. When the body of a rule is acyclic, the translation can be achieved by asserting that it is globally true that when the translation of the body is observed, the translation of the head should be true. We use the implication operator to ensure the inequality in the head with the shared variable z is recognized. That is, the pay proposition must be near the temporal scope of the receipt proposition to enforce their relationship. We presented our translation of acyclic rules as part of a poster last year. Now comes the work in progress, translating rules with cyclic bodies. To achieve this, we decompose the conjunctions of inequalities into a set of primitive constraints. Given a rule with a cyclic body, we enumerate the total orders on the body variables. Then we use this enumeration to enumerate a set of primitive constraints. Primitive constraints are acyclic conjunctions with an implicit total order, where all constants are below some fixed value determined by the rule. Then we filter out constraints that are inconsistent with the rule body. Then, using our translation technique for acyclic rules, we translate each remaining primitive constraint with the rule's head into LTL. Taking the conjunction of these LTL formulas yields a formula equivalent to the input rule. My future work in this area is to prove the correctness of this translation technique, expand the rule language to include multiple shared variables, develop techniques for rules with data elements beyond time, and to study the usability of this declarative rule language for practical applications. Thank you for listening.
Okay, thank you, Isaac. Are there any questions? Okay, Rongu asks, how do you translate the concrete numbers in the timed logic into LTL formulas?
So could I share my screen?
Sure.
So the way that I achieved getting the concrete numbers is I would use a representation of having multiple copies of the next operator or multiple copies of the yesterday operator. So in this case, if you have a constant like 3 or 10, you can encode that by having 10 copies of the next operator or 10 copies of the yesterday operator.
Does this mean you use the next operator for 10 times in this LTL formula?
Yes, that's correct.
Okay, thanks.
Okay, Kim?
Yeah. So I was just curious as to what are the constraints that you allow in these variables. Here it seems to be what seems to me to be what's called difference constraints. So you have one variable which is smaller than another one plus something. Looks like something we do in time automata, where we have these difference bounded matrices. Can you allow more general constraints like 2z minus 4y is greater than 3z or something like that? Or is it always of this form?
So far we've only used something like difference constraints. I've seen that term used elsewhere, but I'm not sure exactly how much that the language that we've designed corresponds to difference constraints. It is true we do not allow 2z minus 3y plus 4x. It's usually different.
Yeah, just a suggestion. Maybe there could be a benefit of sticking to this kind of difference constraint subset, because then you might be able to use some of the data structures for more easy analysis or more easy monitoring. I mean, could be an idea.
Okay, we have time for one last question, if there is one. Okay, great. Then thank you once again, Isaac. And thank you all for attending the CPS session. I think this is the last session for today, if I'm not mistaken. So
yes,
have
indeed.
fun, have a good day.
Yes, it is.
See you tomorrow.
And if you want to
So
hang out,
maybe,
yeah. Go ahead, Dan.
yeah, please, Joe.
No, I was going to say, if you want to hang out in the tavern room, we are going to keep it open till 12 p.m. Pacific time. So it might be a good opportunity to socialize and feel like we are at a real conference. Unfortunately, we won't have any wine or food or coffee, but we'll have each other.
And we have all of that at home. So.
Yeah.
And also what I would like to add, we are looking forward to see you all tomorrow. So tomorrow's session starts at 8 a.m. Pacific time with another keynote, and tomorrow's keynote will be by Tom Hensinger. So quite exciting talk also. I hope to see you all there.
Very good.
Dejan, just a small correction. It's 7 a.m., right? Not 8.
7. Oh, sorry. Yeah, you're right. Sorry.
Yeah,
I'm
for a
getting
moment I
confused
panicked.
with
Yeah.
What is that? So that's like 4 o'clock in the afternoon.
It's 4 o'clock in the afternoon, normal time.
Oh, you Europeans.
I'm joking.
Little exercise in difference, what you hear.
But there's smoke.
It's been very confusing for me, all these, yeah.
Yeah, 7 a.m. California time. Okay.
All right.
All right.
Bye. Thank you, guys.
Bye-bye.
Bye. Thank you.
Bye.
Thank you.
Bye-bye.